Hi everybody, I'm recording this in a different format so I can appear on it, so nice to see you all. Hopefully you think it's nice to see me. We'll see how this goes. This is part 2 of the Radioactive Decay lesson, where we look at a past paper question and see how you might be assessed on your knowledge and understanding about radioactive decay. So let's have a look at this. Exam boards, as I may have mentioned in the past, are notorious for actually bowling you sort of left field questions and assessing your knowledge and understanding in a sort of slightly unusual sort of way, rather than just a standard recall of knowledge. And I think this is a really good question to address those issues and sort of to get you to rethink and apply your knowledge in unconventional ways for that one. So I've sent these out on Frog, so you should have a copy of this. You might want to print it, or you might want to have printed it to write on, or you might write the answers down on a piece of paper, however works for you. But let's have a look at this question. So this comes from June 2013, higher tier physics paper, and it's about uranium-238 and the decay thereof. You can see straight away that it's got a graph. It's not a sort of standard decay series like we did in the lesson previously, but it's got a graph to assess you on these. And it says uranium is an isotope of uranium, uranium-238. It may undergo either radioactive decay or fission. Come to that at another time. The nucleus of uranium-238 is shown as Q in the chart. So there's uranium-238Q. Now we've come across uranium before, and we should know that its mass number, because it's U238, is 238, and also the atomic number of uranium, the y-axis, is 92. So we'd represent that as U, 92, and 238, as we did previously. But we've got various other elements indicated on here by other letters. And the first part of the question says, state 2 letters from the chart which show isotopes of the same element. So you need to work that out. And you write them there. And then explain what happens when Q decays to P. So from what you know, you should be able to actually say something worth 2 marks about that. And part C of question 1, explain what happens when P decays to O. So we've got P decaying to O. So we should know enough about radioactive decay to have a good go at answering that question. The second part of the question, D, or the sort of second different type of question, is says particles released during radioactive decay can have different energies. They can. A suitable unit for these energies is mega electron volts. We don't need to worry about it as a GCSE, but it's proper science. For one type of decay, so for one particular type of decay, the particles released have energies between 4 mega electron volts and 10 mega electron volts. The graph shows how far the particles with these energies travel in air. So how far and travel in air should ring some bells about other learning and properties that you know about for nuclear radiation. Distance travelled is the y-axis. The energy of the particle released in mega electron volts is the x-axis. So it says state the name of this type of particle for 1 mark, so your knowledge should sort you with that one. And then it says use the information in the graph to describe how the distance travelled in air depends on the energy of the particle for 2 marks. Okay, so this is a really excellent physics question with lots of things in it that are relevant and useful for you to think about and cope with in order to answer questions well. Okay, so armed with your printout or piece of paper, pause this video and answer the past paper question. And when you've done that, then start playing again. Okay, so hopefully you've now had a go at the question, you've written it down, you've written your answers down, you've had a good think about it, maybe look things up. This isn't a test, it's about learning, so hopefully you've got some answers to look at. And if we look at the answers here, it says the 2 letters on the chart which show isotopes of the same element. Well, an isotope, by definition, is an element with the same atomic number. So if we take atomic number 92, we've got N and Q. Live on that line as the ones I'd start with, seeing as they set us off on Q. You could also have M and P as well, because they are the same atomic number of 90, M and P, N and Q. Okay, it doesn't matter which way around you write them, but it's the ones that have the same atomic number must be isotopes, because isotopes are the same element with different numbers of neutrons and therefore different mass numbers. Okay, so that first one, hopefully got that one right. Second one, what happens when Q decays to P? Well, Q decaying to P, there, the atomic number reduces by 2. It goes from 92 to 90, Q to P. And the mass number goes down from 238 to 234. So which decay particle has an atomic number of 2 and the mass number of 4 and it is an alpha particle. I hope you spotted that. So Q to P is an alpha decay. And to get both marks for it, you needed to say that you'd recognised that the atomic number or the number of protons had dropped by 2, the mass number had dropped by 4, and therefore that made it an alpha particle or alpha decay. Okay, so that was the answer to that one, and that's why that was the answer to that one. When P decays to O, okay, when P decays to O, we actually increase the atomic number. Okay, the atomic number increases. And the only decay that we know about that is beta minus decay, where a neutron turns into a proton. So the mass number doesn't change because protons and neutrons have the same mass. But the neutron changes to a proton, so the number of protons, the atomic number increases by 1, but the mass number stays exactly the same. So P to O is beta minus decay. Okay, and for the 2 marks here, you say what you observed. The atomic number increases by 1. A neutron changes to a proton would have been nice, not essential, but it would have been nice to demonstrate your knowledge that way. And therefore that is beta minus decay, or beta particle is given off. We really should specify that it's beta minus because we know about positrons now as well. Okay, so hopefully you got both of those marks, but again, we need to aim for getting both of those, not just saying beta minus. Okay, we need both. And the second part, which is pretty left field really, because it's a graph and it's like we don't do this in class and things like that, but the fundamentals of it should be fairly straightforward. Okay, this is the key part of it. The graph shows how far the particles travel in air. Okay, and when you fill in that table, hopefully off the Andy Darville site about properties of radiation, you've got your alpha, beta and gamma and say how far it went in air. Okay, so the name of this type of particle, well, how far is this particle going? It's going between, 2.5 and 10 centimeters in air, that's all. And we should have written down somewhere that alpha particles can travel a few centimeters in air. Beta particles travel tens of centimeters, 10s, 20s, 30s, 40 centimeters. Okay, so this few centimeters tells us that it's an alpha particle. Okay, alpha ray, no, it's a particle, it's a lump, 2 protons, 2 neutrons, it's an alpha particle. Okay, so that was that first bit, hopefully pretty straightforward. Secondly, sorry about flicking backwards and forwards, use the information from the graph, so the graph, the shape, the axes, the numbers, to describe how the distance travelled depends on the energy of the particle. And hopefully we're all at least decent mathematicians to recognise the sort of correlation it is like that. Okay, it's a positive correlation. As the energy of the particle increases, the distance travelled increases. And the mark scheme says any 2 of these, one increases as the other. I would hope you'd actually said specifically what the energy, as the energy increases, the distance increases. Again, as I've always said to you, where there are numbers to be quoted, please quote the numbers. Okay, and you can say that the range gradually increases with energy. It's not perfectly linear, is it? There is a slight curve to that trend. So you should really spot that one and say it increases. It's not a linear trend. It's not a straight line correlation of positivity, but it curves upwards. By quoting the values on the graph, you're actually taking that into account. Okay, so hopefully that was a successful past paper question and you wouldn't be fazed by something as unusual as that if it happens in the exam. And just to finish with, seeing as you obviously want to show your knowledge and prowess at nuclear decay, don't pause it before you have a go at these. I've got to show them to you, but when I show you these, have a look at these problems, these decay series, look at them, pause the video, work out your answers, and then I'll reveal all when you've unfrozen it. Okay, so these are a question, what were the parent elements for these decay series? Beta minus and radium, I should say, positrons, alpha particles. So these are the products, the daughter product and the emission. What was the starting point? What was the parent for those? Okay, so see if you can work those out, pause the video, and then all will be revealed. Okay, hopefully then you're ready to see what comes next. These are the answers. hopefully you've got and looked up on your periodic table that those are the answers for those decay series. And if we've managed to get those right, and it's a question of right wrong really, so if you've got your numbers sorted and you know your decay series and how we get beta minus decay, how you get positron decay, alpha's easy. And then we're up and running, and you can put a big tick next to your understanding of radioactive decay. Okay, so well done, more to follow.